All right, so let's take a look here at example number 2. For what values of x does this series converge? Again, if I'm thinking of this like a function, and that's an infinitely long polynomial looking thing, what are the x's I can plug in to get a convergent result, and what are the x's that I can't? Now, here's where a lot of our chapter 5 knowledge is going to become really, really useful. What we're going to actually attempt to do is to use one of our tests from chapter 5 to help us answer questions about these domains of these sorts of new power series functions. Here's what we're going to go ahead and do. I'm going to say that we will use the ratio test to help answer this question. So let's see what we come up with. I'm going to go ahead and start by saying that we calculate, and when I do my ratio test, remember I have a limit. It's going to be as n goes to infinity, and I'm going to have to set up like an n plus 1 factorial over an x to the n plus 1. And then I'm going to have to do that over an n factorial x to the power of n. And remember that each of these would be positioned in absolute value bars. Now, the cool thing here is that I can simplify these absolute value bars down, but I got to be a little bit careful in the way that I do it. Notice that the n factorial stuff is never going to be negative, so I don't have to worry about that. And x to a power may or may not be negative. It kind of depends on the power, but it also depends on what you're plugging in for x. Notice though, if x is positive, then there's absolutely no way that the top or the bottom could be negative. So here's how I believe that I could go ahead and attempt to simplify this. I think it's totally possible that we could simplify this down into the following. We could simplify the top into an n plus a 1 factorial, and then an absolute value of an x raised to the power of n plus 1. Notice if I absolute value the x before I take the power, I'm going to get the same number. I'm just going to make sure I always get a positive result of that same number. Same thing in the denominator. I can do an n factorial and then an absolute value of x to the n. But now I can simplify this up, and you can see what I'm going to come up with here. My n factorial stuff is going to simplify down to an n plus 1, and I'm ultimately going to be left with an x to the power of, an absolute value of x, ultimately to just the power of 1. So at this point, I can go ahead and I can start to see a couple different things. If it's the case right now that I want to evaluate this limit, I should note that the only thing in the limit at the present time that's moving is the value of n. X in there is technically just a constant. So I'm going to go ahead and break this down really quickly into two key parts. What if x, the number I'm plugging in, is a 0? Well, if that's the case, then my limit here of my n plus 1 times my absolute value of x would turn into just 0, right? Because I'd have just limit of 0. And so I would have a result, I would have a result of the ratio test that comes out less than 1. And so the series converges. So if I plug in the number 0, I definitely get convergent. Now that's maybe not too big of a surprise if I was to go back up here and take a look at what the series actually looks like. Really quickly, I just want to highlight what happens when I take a look up above at the series. If I was to write out some of the terms in this polynomial, I would see that I end up with a 1 at the start, and then I'm going to end up with a x to the power 1, and then a 2 x squared, and then a 6 x to the third, and so on and so forth. You could double check me on those values. But again, obviously if I plug in 0, is that going to all add up to something? Of course, it's going to add to 1. No surprise that this converges. Notice though, if I plug in anything else, if x is not a 0, then I could see that the limit as n approaches infinity of n plus 1 times the absolute value of that x is really just going to be equal to Let's see, if n's going off to infinity, isn't that just going to turn into infinity? And that's obviously greater than 1. So by the ratio test, the series diverges. So I can kind of see something here. As a conclusion, the series only converges when x is equal to the number 0. If you plug in anything else into this addition problem, you will end up with a divergent result. So this sort of a weird green function that I have up here is actually going to have a very simple picture, because when I try to graph this function, it's only going to be when you plug in 0, you get back 1. And when you try to plug in any other number, you don't get an answer. So boom, there's the picture of my series here, or this weird infinitely long polynomial thing. All right, in the next video, we'll take a look at example 3, where I'll ask you to try to play around a little bit with this same sort of idea, and then we'll almost be done with this section.